I know where there's some, right here in the hall closet.
No, Molly, not in there. I'll have a look.
Hello and welcome back to Fibber's Closet. We have a new project on the bench. The inside bench because it's cold upstairs. It's Heathkit vintage early 60s condenser checker. This is the C-3 model. I've wanted a capacitor checker for a while, and this one became available, so I bought it for a good price, I think. I'm hoping that it's all original inside. We'll see. You can test either resistors or capacitors with this. You can check leakage on electrolytics. You can stress test the capacitors with a 450 volt leakage test. What else? Has a magic eye. I don't know if it works. We'll find out. It's a very lightweight unit. The aluminum body case has seen much better days. A lot of the paint is flaked off and it's dirty. So I'll strip this and paint it battleship gray again. Looks like it has a metal finish on it. Wrinkle finish. Sure I could find something. The handle has the words Heathkit Precision right there. So we'll see. I'm expecting it to be pretty simple inside. Let's take a look. Mostly I hope that it's not been messed with in here. We'll see. Okay, this should, yeah. The case slides off the instrument itself. I'll go ahead and remove this and get it out of the way. Well, some years of grime down in the bottom of that, but that'll all wash out. It'll be easy to clean up. It still has its original feet. Amazing. We'll set that aside, and here we have it. It's a rather simple device. Power transformer, which I hope is good because I imagine it would be hard to replace. 2 tubes. Magic eye is here. Boy, that's not a great mount. The builder, the original builder, left himself or herself lots of notes on the inside. Front A1, 2, 3, 4, 5, 6. F down here. M over here for the magic eye. It looks like it might have been in a damp storage space. There's this kind of moldy looking stuff on the wires. And on this component right here, I can't even tell what it is. It's got so much fuzz growing on it. But it looks pretty clean. Pretty clean. The underside, we have a bunch of electrolytics. And it all looks original. Although this Astron, I'm not sure about. I'm not sure. That's that body shape suggests it's a modern cap, but by the 60s, they were still putting these paper caps inside plastic containers. There were still waxy paper caps inside plastic containers. Oh, got a wire has been broken off from somewhere. Huh. I don't see at first glance where that goes. I don't know. All right. The two tubes are this one is aged into place. It's a CRC 1626. That says RCA. And I have the schematic right here. Yeah, in 1626. It's interesting what they chose to do with this 1626. It's a triode. As you can see, has a grid, but the grid is tied directly to the plate. So this is acting as a diode. They've used the 1626 triode and wired it as a diode, so it's the rectifier for the power supply. The other tube, the only other tube, is this Magic Eye 1629 right here. And I don't know a lot about Magic Eyes. I'll have to do a little bit more research on how they work, but we'll do that as we go along. Otherwise, it's a relatively simple schematic. It measures using bridge circuits, which are a bridge circuit fundamentally is if you have resistors with, if you have 3 resistors with known good values, or 4, you can add another one and know its value through mathematics. So that's through mathematics, which is true, but through how much current and voltage the unknown resistor uses or drops. Same thing with capacitors. You can bridge, you can put a fresh capacitor, an unknown capacitor inside a network of known capacity values and figure out what the unknown capacitance is. Yeah, pretty straightforward. As we go through this, as I start to put it back together, we'll explore this in more detail and talk more about how these bridge circuits work. So the second tube, and I think my tube tester will check these guys. My Heathkit tube tester will check these guys. Second tube is this Magic Eye. That looks kind of precarious to me. Look how that tube is sitting at an angle like that. It's this bracket right here is too close to the front panel of the instrument and is tipping this bracket back. I don't know if you can see that. Yeah, maybe right there. That causes this to slope up, and the Magic Eye is hanging out the front. I think, now that I look at this, usually this is just a spring clip. Usually that spring clip goes around the base of the tube, not the glass. I think this bracket was put in backwards. I think this part should be going this way, holding the spring part around the base of the tube. Interesting. I'll have to look at the assembly instructions and see what they say about that. Oh man. These haven't been out in a while. This one is another RCA, original tubes, 1629 Magic Eye. Again, I don't know if this one works. The tube tester will tell me, and that's the first thing I'll do is just check these two tubes, because I don't have anything like this. These are still available here and there. But I'll check these. If these are flawed, I'll have to order new ones. I don't have anything in my stock like this. It's funny they used a triode for a diode. Anyway, that's the first step. So this is our new project. We'll once I test the tubes, I'll get back to you, and then we'll run our normal tests on the power transformer and see if it's sound. And then we can begin to clean this up and replace fuzzy parts. Okay, be back in a minute. Right, at this point I've tested both the 1629 Magic Eye tube, and it works, I'm happy to say, and it glows brightly, so that's a good sign. And I've also tested the 1626 triode, which also tests out fine, and cleaned them both up. So I'll set those guys aside till we need them. The next thing I want to do is test the power transformer. As you can see on the schematic, the primary of the power transformer on this side of the schematic simply connects to the wall, the plug-in. Switch closes, and then the plug-in is right across the primary of the power transformer. So all I have to do, let's see, make sure I know where the on-off switch is. That's AC off. Okay. Is put the ohm meter across the two prongs of the plug-in, the wall plug, and turn the unit on. What I should be seeing right here is 0 ohms. Like that. Oh wait, these are so corroded. So another idea is to go to where the line cord comes in, which is right here. These two, this tag strip with these two units on it. This yellow switch goes up, I think, yes, to the on-off switch. So I'll try the same thing, but back here I'll go right across where the power cord enters the chassis. Hook in there, yeah. So now we've got, what is that? That's K ohms, but no, so 40 ohms. 57 point, this is not an auto-ranging multimeter. So 58, we'll call it 58 ohms across the primary, which sounds about right to me. So I'll make note of that. Also, if I turn this AC off, that should go to infinity again, which it did. So that means the switch is good, and that means the primary has 58 ohms DC resistance across it, and I'll make note of that. Alright, I've discovered that the power cord had an intermittent open right here where it's bent, and it's old and stiff anyway, so I'll replace it. So I cut it off to get it out of the way. Now we'll check out the secondaries. There are 3 secondaries on this power transformer. Filament, one for the tube filaments or heaters. I'm not sure what this one is for, but it says 55 volts AC. And then here's the B plus voltage, and it's interesting. It's a 500 volt winding, and then it has 2 power filters wired front to back in series with chassis ground going in between them, so that you get minus 400 volts DC on this side and 150 volts positive on this side. So we'll start there. I have to identify which capacitor this is right here for starters. And these are the 2 power caps right here. Here's the ground end. This one has gunk extruding out the back, so they're both, no, that one has even more gunk coming out the back, so they're both shot. Needed to be replaced anyway. We'll try that again. The 500 volt AC winding secondary has one pin, one side goes to pin 3 and 5 of the 1626, which is right here, and the other side goes to the negative side of one of our power filters, or power caps, which then goes to ground. So this power cap goes to pin 8, looks like. Yes, there's the marker. This power cap goes to pin 1, rather. This power cap is going to connect it to pin 8. So this one is this uppermost filter cap, this 150, or this, for this 150 volt DC line. The other one, oh, pin 1's just a tie point. Okay, so here are the 2 leads coming out of the power transformer. One's going to pin 1, the other's going to pin 3, and then to 5. So that's these 2, and then we have this lead and this lead from the power transformer going to pin 2 and pin 7. All right, here's the data sheet. Pins 2 and 7 right here are for the heater, for the filament voltage. So we can check that that winding, the yellow windings, on the secondary, the filament secondary, using pins 2 and 7, just a DC resistance between those 2. The tube is out, so the filament itself won't give us any reading, but we will get the secondary winding. And then, what else were we looking at? Oh, I said pin, capacitor was going to pin 1. Yeah, so pin 1 is just a tie point on the circuit board. Pin 1 isn't used for anything. Pins 1, 4, and 6 are NCs, no connection. So they just use that as a convenient place to tie 2 or 3 wires together. Looks like they probably did the same on, no, 6 is bare. 4, 1, 2, 3, 4 is bare rather, and 6 is bare. So they just did that on pin 1. They used pin 1 as a tie point. So we'll check the filament winding first, since it's so handy right there. Go from pin 2 to pin 7 on that tube socket. Yeah, we got 2.6, 2.7 ohms. That's about right. I will make note of that in the schematic. So we know that pin 1 of this tube socket is being used as a tie point. And we know that pin 8 right here is not a tie point. It's not just a tie point. It's the cathode for the in this case they're using it as a rectifier, but the 1626. So we can go to the other end of the other power cap right down here and pick up this red lead. And the other end of the other power cap happens to be pin 1 of the tube, because that's where this tie point is. This tie point right here is pin 1 of the tube. So we can go from pin 1 right here to pin 3 of the tube of the 1626 and pick up the DC resistance of this secondary. So pin 1 right here, if I can grab it, and then pin 3 is right here. Whoops, came right off, didn't it? And pin 3 is right here. 3 and 5 are connected together. So we have a DC resistance of 1.79K, which again for a high voltage winding makes a lot of sense. There's a lot more wire in the high voltage winding to create this 500 volt AC secondary than there is to create a 12 volt AC secondary. So this is 2.6, this is 1.8K right here. And so I say that's good. Make note of that. And now for the third secondary, this 55 volt AC secondary, I'll have to do some, the wires, when they were put in, you could tell what color they are. Now they're all beige, this brown color. The original color is faded away with time. So I'll have to chase these down to pin 9 of the rear deck front side of this switch, and the other one goes to pin 7 of this switch, the leakage test switch. So I'll have to chase those down, or if I can find this potentiometer right here. But in either case, I'll have to chase that down. So I'll be back in a second. I have finally found the correct connections on the correct switches for this. So I have the ohm meter set across the 55 volt AC lines up here on this switch and down here on this switch, and we're showing 223 what's that, K.223, so 223 ohms. And again, that's about right. This very low voltage, 12 volts, is a low number of windings. Medium voltage, if you will, 55 volts, has 223 ohms worth of wire, and this one, the high voltage one, has 1.8 K ohms of wire wound in it. But they're all good, so I'll make note of this one. It's 223 ohms, and we're good. All right, maybe you're asking yourself, why didn't I just plug it in, see if it works? Well, I never do. I never do, for a couple of reasons. In power supplies, I never do, because the filter caps, the electrolytics, are probably shot in any electronics of this vintage. And if one of these guys, or both of them, worst case scenario, they've turned into resistors. They have leakage. They leak DC volts across themselves. And when you get a leaky capacitor, or two leaky capacitors in this case, what you can do is cause this rectifier tube to melt right in front of your very eyes. It'll draw so much current through it that it will just melt down and destroy it. In radios, the same thing can occur if you just plug it in with existing electrolytics in it. The odds are that you might get lucky. The odds are that you might not get lucky and might in fact blow out your rectifier tube. The other capacitor that I always check in radios is the coupling cap between various stages IF, from one IF to the next. A coupling cap from the last IF to anywhere. Coupling caps between tubes, same problem. They invariably couple the signal on a plate to the grid of the next stage, and if that capacitor is turned into a resistor, it's going to melt down one of those tubes. So that's just not something I want to do. So it's easy for me to check them, and I check them. Then if I'm confident that everything's okay, I'll turn it on. Right now I'm confident that the power transformer works. I'm not confident that these capacitors, in fact I'm confident. We've seen how leaky they are already. You can see stuff oozing out the back here and here. So I know they're bad. I know they're leaky. So I'm going to replace those guys. And since I'm in the replacing cap business, I'll get rid of these waxy paper caps too. These guys always fail. They just do. And this, even though it looks like it's a plastic cap, is probably a paper cap in a plastic cap housing. Same with that one. So all of these have to go, and I will do that next before I power it up, just to make sure that everything survives the power up, which is the goal. The goal isn't to melt this down. The goal is to bring it up. So that's it for this one. I will undertake the replacement of these capacitors and then start checking resistors, because the resistors have to be pretty precise, pretty right on. Although these are all marked as silver. That's, what is that, 20%? Yeah, I think that's 20% tolerance. Those guys are up here also silver, so they're 20%, not bad. But carbon, it's carbon composite resistors all tend to go up in resistance over time. Some of them go up a lot in resistance over time, so I expect to have to change several of those as well. But I'll get started, and I'll see you next time. Take care.